Okay, today we'll be looking at a few concepts of acids and bases. I'm first just going to quickly go through the basic principles, and then I'll explain in more depth the little more difficult parts. So, in your textbook on page 308, you have to know these acids, their formulas, their names, and whether they are weak or strong, as well as at least one use of each. And then also the weak acids on page 309, you have to know the name, the formula, whether it's a weak or strong acid, and what it's used for. Bases, the same. You have to know whether it's strong or weak, what's its name, what's its formula, and one use. Then you also have to know the two main theories on acids and bases. So the Arrhenius model of what acids and bases are. According to Arrhenius, an acid is a substance that releases hydrogen ions in aqueous solution, and a base is a substance that releases hydroxide ions. So just note, hydrogen ions H plus can also be written as H3O plus, like that. H3O plus or H plus, those two both act as the acid molecule. Then the Lowry-Bronsted definition. Yeah, an acid is a proton donor. In other words, it's going to release its own hydrogen out of that compound. And a base, a Lowry-Bronsted base, is a proton acceptor, so it's going to take a hydrogen. Okay, so in this example, that NH3 acts as a base because in the product it has gained one hydrogen. Okay, then on page 312, here at the top, they distinguish how ethanoic acid and sodium hydroxide would react in water. But what they refer to here is dissociation of a strong base. So you just have to remember the difference between what a strong base is and a strong acid and a weak base and a weak acid. Okay, so you need to distinguish between what strong and weak means and what diluted and concentrated means. This does not mean the same thing. So strong base or acid ionizes completely or almost completely in water, which means it releases a high concentration of ions in solution. If you remember from grade 10, the higher the ion concentration, the higher the electrical conductivity will be of that ionic solution. Okay, so in other words, a strong base or acid that is ionized almost completely in water will conduct electricity easily because of its high ion concentration. A weak base or acid ionizes very little, if at all, in water. So in other words, it releases a very low concentration of ions in a solution. So again, because you have a low ion concentration, it's not going to conduct electricity very well. Then, a diluted base or acid. You can either have a strong base or acid that's diluted, or a weak base that's diluted, base or acid. So diluted just means you have added water to it, or you have added it to water. Then it's diluted. Concentrated, you can have a strong concentrated acid or a base, or a weak concentrated acid or base. That's when you don't have any water or very little water that has been added to it. I'm still on page 312. So now the distinction between a monoprotic and a polyprotic acid. Mono just means one. Protic comes from protons, that's hydrogen. Poly meaning many, protic as in proton as in hydrogen. So monoprotic acids are just acids that release only one hydrogen. They have only one hydrogen to release. For example, HCl, hydrochloric acid, there's one hydrogen. A polyprotic acid can be diprotic, which is 2, or triprotic, which is 3, etc. So an example there of a diprotic acid would be sulfuric acid, H2SO4. This becomes important whether it's monoprotic or polyprotic when we have to determine the hydrogen ion concentration or the pH of a solution. Then conjugated acid-base pairs. This is on page 315 and 316. So when you have an acid and a base reacting, the acid, according to the Lowry-Bronsted definition, will donate its hydrogen and the base will accept the hydrogen. So on the other side, we'll have a molecule that's exactly like the acid, only it has one less hydrogen. And we will have a molecule that's exactly like the base, only it will have one more hydrogen. So a conjugated acid-base pair is a pair of molecules that differ from each other by only one hydrogen, okay, on both sides of a reactant. So it's a reactant and a product that differ from each other by only one hydrogen. So to make it easy, we just call all of the reactants the acids and the base, and the products would be the conjugated base and the conjugated acid. Page 319, amphilites. An amphilite is a substance that can act as either an acid or a base. And then, yeah, as an example, they give you water, where water in reaction with ammonia is going to release its own hydrogen to give ammonia its hydrogen. So their water acts like an acid. But in reaction with hydrochloric acid, the water is going to accept the hydrogen from hydrochloric acid, and therefore, because it acts as a hydrogen acceptor, it acts as a base. So in this example, you can see water is an amphilite because it can act as either an acid or a base, depending on what it reacts with. Just a note here on page 321. On this table, you can see that if you have a strong acid, the conjugated base of that strong acid will be weak. And if you have a weak acid, the conjugated base will be strong. So if you have a strong acid, that will give you a weak conjugated base. If you have a weak acid, that's going to give you a strong conjugated base. Okay, now hydrolysis, page 322. So hydrolysis happens when water reacts with the ions in a salt solution. Okay. The general reaction there would be that an acid and a base would form salt and water. Now, this is important for you to be able to write down a hydrolysis reaction. So if you have an ion in water that forms H3O plus, then that's going to be an acidic solution. If you have an ion in water that forms OH minus, that forms a basic solution. Okay, those that don't react, they are called spectator ions. And those spectator ions, if they are negatively charged, they are usually conjugate bases of strong acids. And if they are positively charged, they are usually conjugated bases of strong bases, of strong acids. Sorry. Okay, that should be acids. So if you look at this example, sodium carbonate is a base. So that's going to form CO3 and sodium. And now CO3 in water is going to form OH minus. And the moment you have OH minus, then you know that you have a basic solution, an alkaline solution. All right, then on page 326, reactions of acids with metals. There are 4 basic options that you could have with metals. So if an acid reacts with just a metal, like anything on the left side of the periodic table, on the left of that step, for example, calcium or lithium or sodium, just a plain metal, then your product is going to be hydrogen and salt. Now that salt is always going to be from the metal and from the acid. So the metal is always positively charged, right, when it becomes an ion, and the acid will always have a positive hydrogen with a negative ion. So that could be HCl or H2SO4 or any negative ion that's bonded to a hydrogen. So that hydrogen is now here, right? And the salt will now consist of the metal plus the negative ion that comes from the acid. So everything in the acid that's not the hydrogen, because the hydrogen went there. Okay, so that's what the salt will consist of. So if that was HCl plus lithium, this will be lithium Cl and hydrogen, right? So the salt will always be, all of them will be the same thing. It will be the metal plus the negative ion that comes from the acid. Right. Now, this reaction between the acid and the metal oxide. So now you have oxygen bonded to the metal. So let's say that's, for example, lithium oxide. Now you're going to have water and the salt. And the salt is again going to be the metal plus the negative ion of the acid. Okay, so those two will form the salt and these two form the water. If you look at that. Here again, metal hydroxide, like calcium hydroxide, for example. The acid is always a hydrogen with a negative ion. So this and this together will form water, and this negative ion and this metal together will form that salt. Acid with a metal carbonate. Yeah, your product will be water plus carbon dioxide plus the salt. And the salt will again be this carbonate with this Sorry, not the carbonate, the metal with the negative part, negative ion of the acid. So those two will form the salt. The CO will form carbon dioxide, and the other oxygen will go there to form water. So with these reactions, you have to remember, you have to study this general equation, and then you have to be able to complete the reaction for specific acids and specific metals. Okay, the bottom of page 327, neutralization reactions is any reaction that occurs between an acid and a base to form a salt and water. So that's a definition that you also have to know. Okay, then indicators on page 338. You have to know, in order to be able to answer all the questions in titration reactions, which I will still go through with you, you have to know which indicator changes color at what pH. Okay? And you also have to know the colors. So what color is it in acid? What color is it in base? So I have found it easiest to draw myself a pH scale like this. You know, the pH scale goes from 0 to 14. 0 is the strongest base, strongest acid. 14 the strongest base. 7 is neutral. So if you then, on a pH scale like this, you draw methyl orange changes color there from 3.1 to 4.4. Methyl red changes color there from 4.2 to 6.2. Bromtomol blue changes color from 6 to 7.8. Phenolphthalein changes color from 8.3 to 10. And you make it the colors that they become. Methyl orange is orange and yellow. Methyl red is red and yellow. Bromtomol blue is yellow and blue. And phenolphthalein is colorless and pink. Okay. Okay, so what you have to be able to do with knowing that is you need to combine your knowledge of the colors and the pHs of the color changes of indicators. That knowledge you have to combine with knowing which are strong and which are weak acids and bases. Okay, so now what will happen is you will have, let's say for example, you could have a strong acid that reacts in a neutralization reaction with a strong base. Okay. And you know that that will always form water and a salt. Okay. Now, on the pH scale, where we have 7 there where it's neutral, 0 at a strong acid, 14 at a strong base. Now, when you have a strong acid that reacts with a strong base, those two are going to neutralize and meet each other somewhere in the middle of their two pHs, close to 7. Right? So that means in order to see when this neutralization reaction has taken place, you are going to need an indicator that changes color in the vicinity of 7. And that is bromtomol blue. Okay? So that's why you have to know at what pH which one changes. Okay, and then you have to know the color change will be between yellow and blue. Okay, depending on whether you had it originally in the acid or whether you originally had it in the base, would depend on whether it's from blue to yellow or from yellow to blue. Okay, now if we have a weak base or a weak acid that reacts with a weak base, so something here that's not too far away from 7 either side, and these two react, they will again meet each other somewhere in the middle of their two pHs, which will always also be close to 7, in the proximity of 7. So again, we need an indicator that will change color close to 7, which will be bromotamol blue. Then, if we have a strong acid that reacts with a weak base, these two will neutralize and they will meet each other somewhere in the middle of their two pHs. And if you look at this scale, you can see that it's somewhere below 7. So that will be one of the two methyls, either methyl red or methyl orange, that you will use depending on what the pHs were. Okay. Then, if we have a weak acid that reacts with a strong base, these two will neutralize somewhere in the middle of their two pHs, and you can see that it's on the right side of 7, between 7 and 14. So that would mean that you would then use phenolphthalein, because phenolphthalein changes color on the base side of the pH scale. So that's why you would need to know which indicators change color where. So whether it's a strong acid and a strong base, or a strong acid and a weak base, or a weak acid and a strong base, or a weak acid and a weak base. So again, when the two strong ones or the two weak ones meet, you're going to need bromotamol blue. If you have a strong acid and a weak base, then you're going to need one of the methyls, either methyl orange or methyl red. And then if you have a strong, this is what you would need if you had a strong acid and a weak base. Then they would meet each other on the acidic side. If it's a weak acid and a strong base, then you would need phenolphthalein. Okay. Okay, now the last bit of theory before I start talking you through all the calculations is on page 373 in your textbook, the applications of acids and bases in the chloralkali industry and in the hair industry. So just read through that. It's quite straightforward. Okay, now we're going to start with the calculations. So the first calculation is determining the concentration of a solution. Okay, so this you have done in grade 11. So I'm just going to remind you of the formulas we use. So you remember that N is equal to M over M, where N is the amount of moles, M is the mass in grams, and capital M is the molecular mass of a compound. So for the molecular mass, what we do is we add the atomic masses of the individual elements. Okay. So, for example, let's say we need to calculate the molecular mass of H2SO4. The molecular mass of hydrogen is 1, but there's 2 of them, or they're the atomic mass. So there's 2 times 1. Plus the molecular mass of sulfur is 32. Plus the molecular mass of oxygen is 16, but there's 4 oxygens. So that would be 4 times 16. So when we add all of that, we get 98 grams per mole. Okay. Mass would be given in grams, N given in moles. Okay, so that's the one formula we need in order to eventually calculate concentration. And then concentration is equal to N over V. N is M over M, right? So because N is M over M, we can also, in the place of N, substitute M over M. So that would mean C is equal to M over MV. Okay, where C is now the concentration of a solution, and that is measured in moles per cubic decimeters. When you write the unit, you have to write it like that. When it's given to you in an exam, they could just give it to you as capital M, but you may not use that when you give an answer. Okay, so this stands for molar. Molar means moles per cubic decimeters. Okay, N is mole again. And V is the volume, which is measured in cubic decimeters. Okay, the SI unit is cubic decimeters. So if they don't give you the moles, they give you the mass and the molecular mass, then you have to use M over MV to get C. All right, so that's how we're going to calculate concentration. There are examples in the textbook, so you can just work through them. Okay, then preparing a standard solution. A standard solution is any solution with a known concentration. That's also a definition you have to know. A solution with a known concentration. So yeah, they can just ask you questions in which they tell you what the solution's concentration needs to be, and then they'll ask you, so what is the mass of powder that you need to put in a certain volume of water? Okay, so basically, in order to prepare a standard solution, you are still just going to use N is equal to M over M, and C is equal to N over V. There are also examples in the textbook of how to do those calculations. Okay, then dilution. So if we have a certain concentration of a certain solution, we'll have a certain volume of that concentration. And now we want to change that to, let's say we want to change it to a lower concentration. So you have this volume with a very high concentration, and now you want a different volume, but you want a lower concentration. So in order to know how to do that, or what volume you need to add, we use this equation C1V1 is equal to C2V2, where this is the initial concentration, which is measured in moles per cubic decimeters. This is the initial volume, which is measured in cubic decimeters. This is the wanted concentration, so the final concentration in moles per cubic decimeters, and the final volume that you want in moles in cubic decimeters. All right. Now, you need to remember that this is the volume, the total volume you have after adding water. So this is not how much you add. This is the amount you have after adding water, the volume you have finally. So if you need to give the answer, how much would you need to add? You would have to subtract how much you have in the end from how much you had in the beginning. So in questions like this, please make sure that you read the question and see, are they asking, when they give you the question, are they telling you what the final volume is, or are they just telling you how much you add? So if they tell you how much you add, you have to take initial volume plus how much you add to get that. If they tell you what the final volume is, then you can directly substitute that. Okay. There are also examples in the textbook of how to do calculations like this. Okay, I am just going to do this one example because the examples in the textbook are not many. So, for example, of dilution, determine how much water should be added to a 200 milliliter solution of 0.8 moles per cubic decimeters in order to change the concentration to 0.5. So, firstly, we have to identify this as a concentration by its unit. That's important. And then 200 milliliters, what you need to know here is that a milliliters is equivalent to cubic centimeters. And cubic decimeters is equivalent to a liter. So if you have 200 milliliters, 200 cubic centimeters, it means you have 0.2 liters, right? If you have 200 milliliters, you have 0.2 liters. So if you have 200 cubic centimeters, it means you have 0.2 cubic decimeters. So the first thing we do is we convert to SI units, right? Now, we know that C1V1 is equal to C2V2. They tell us, determine how much water should be added. So we need to find the final volume and then subtract from the initial volume. To a 200 milliliters, so we're given the volume. We're given the concentration to change it to another concentration. So in that formula, we only need that one unknown. So to substitute in there, concentration, initial concentration is 0.8. The initial volume is 0.2. The final concentration has to be 0.5. And we want to calculate the final volume. So then we get that V2 as 0.32 cubic decimeters. But that was not the question. The question is, how much water should we add? So that means we need to add what we have finally minus what we had initially. So that's 0.12 cubic decimeters of water that we need to add to the original solution to give us that new concentration. Okay, now talking about titration. Titration is actually what the whole acid-base chapter is about. So here's a picture of a person busy with a titration. So this here is called a burette. I'll write down all the names now. So if you look carefully, you will see that the burette has little lines of measurement on it that measures every milliliter that you use. Then here at the bottom, it has a little tap that you can open and close. Underneath the burette, we would have a beaker, a measuring beaker that in which you can also measure volumes. And then this thing that holds the burette is called a retort stand. Okay. So inside this beaker, we would usually put the base here in the burette, and then the acid that we are going to titrate with. I'm going to explain titration now. We would put the acid down here in this measuring beaker, and then we would add the indicator here. And the indicator would be determined by whether it's a strong acid and a weak base, or a strong base and a weak base. Like that is how we would determine what's the indicator there. And then this base that's in here, we would open the tap. We would first fill the burette to the 0 point here right at the top. So this burette measures how much we have used, how much of this base in here we've used. So if it's full, then it would be at 0. And then as we open the tap and the base runs out through the tap into the beaker, reacting with the acid, this measurement would obviously increase 1 milliliter, 2 milliliters, etc. Okay. So by the time it gets over here, that would be 50 millimeters. Usually, if this is a 50 millimeter burette. Okay. So titration is just a neutralization reaction between an acid and a base that happens in this beaker. But the titration, we call it titration because we are measuring how much of this base we use. And we use this measurement we have here. So we have a known volume of base used. We have a known volume of acid used, and then one of these two have a known concentration. Either the base will have a known concentration or the acid will have a known concentration. Then we would use the known variables to calculate the concentration of the unknown substance. So if we didn't know what the concentration of the base was, we would use these measurements to determine this concentration. Or if we didn't know the concentration of the acid, we would use these measurements. Okay, so just again, this is a burette. I'll write down the names now. This is a retort stand and a measuring beaker. Right, so you're going to need a retort stand, a measuring beaker. So you're not necessarily going to measure the acid that you put in the measuring beaker with this beaker. You're going to measure it first with a measuring cylinder, which is usually a bit more accurate, and then you'll just pour it out of the measuring cylinder into the measuring beaker so that you can do the titration. And then the main thing you need in order to measure how much of that base you are using is a burette. Right. So I will also post you a video of how the titration works and where somebody is performing a titration. So what's going to happen is eventually, if this is our burette with our little tap over here, then the base is going to drip into this acid until a color change happens. And the moment the color change happens, then we know that we have reached the end point of the titration where neutralization has taken place. Neutralization doesn't necessarily mean it has gone to pH 7, right? It just means that on the pH scale, this, let's say, strong acid and weak base have met each other in the middle of their two pHs, right? Okay, so now before we can start with the calculations, you are going to have to be able to complete a reaction. So usually that reaction is a reaction between an acid and a metal, which would either be a metal or a metal oxide, metal carbonate, or metal hydroxide. So we've already gone through how which products will form. Then the second thing, which is extremely important, is after you've completed the reaction, you have to balance the reaction. Okay, because a balanced reaction tells us if A reacted with B to form C and D, what were their ratios that they reacted with. Let's say the ratio was 2 to 3, and there we also had 2D that formed, right? So these ratios are what we need in order to do the titration calculation. So after you've done that, now you can go to the formula that says Na over Nb, I'm going to explain it now, is equal to CAVA over CBVB. Right. Now, this means the mole ratio of the acid. The mole ratio of the acid as in the balanced equation. All right. Then this Nb is the mole ratio of the base as in the balanced reaction, right? So you see, we can't do any of these calculations without having balanced first. Okay, now Ca is the concentration of the acid, and one of the two will be known. Either the concentration of the acid will be known or the concentration of the base will be known. And one of them will be unknown. That's why we're doing this whole calculation. So this is the concentration of the base. Va is the volume of the acid used. So usually that would be the amount of acid that we had put there into that beaker, and then that would be the volume of the base used, and that we would measure in the burette. Okay, it doesn't necessarily have to work like that. We could have had the acid in the burette and the base in the beaker. The base or the acid sometimes, especially weak acids, form crystals, and then those little crystals block the burette. That's why we prefer not to put the acid in there. Okay. Because it blocks the tap, because the tap of the burette is very, very small, the little hole for the acid or the base to run through. Volume, is measured in cubic decimeters. Okay. The burette is in cubic centimeters, so you will probably have to convert there. Or you'll just have to convert the final answer No, you're going to have to convert, yeah, because this is cubic decimeters, so you can't work with cubic centimeters and cubic decimeters in the same calculation, except if you really concentrate. But okay, just remember that this is cubic decimeters, but this is usually in cubic centimeters. So somewhere you're going to have to convert either there, or you need to focus so that you convert it correctly in your final answer. Then you're going to have this from the balanced equation, and then one of these will be unknown. So you could also write this formula as NB over NA is equal to CVBV over CVA. You see the difference? Yeah, A is at the top, yeah, B is at the top. So you put the one at the top that's unknown. Okay, so if that one is unknown, if it's the base that's unknown, you just put the whole equation, you put the base at the top. If the acid is unknown, then you just, for the whole equation, you put the acid at the top. That just makes the whole maths easier. Yeah. Okay, so then from here, all you do is you substitute and you get that unknown. So there are also examples in the textbook of how to do those calculations. So please just work through them. I just want to add here that they won't necessarily give you this concentration. They could tell you how they made it and tell you that they used a certain mass of a certain substance that they put in a certain volume of water. And then you have to use that information to determine the concentration with this formula first, and then substitute this answer into here. Okay, now equilibrium constants in your textbooks, it's on page 364. We are doing acids and bases now before we've done equilibrium. But in equilibrium, we determine what is called an equilibrium constant. How that works is equilibrium constant is K. In this case, because it's an acid, we're going to say the equilibrium constant of an acid, or the equilibrium constant of a base, or the equilibrium constant of water. So an equilibrium constant, in all cases, is always the products, the concentration of the products, to the power of their balancing numbers multiplied by each other. So product 1 to the power of its balancing number multiplied by product 2 to the power of its balancing number, divided by the reactants, the same, reactant to the power of its balancing number multiplied by the other reactants to the power of their balancing numbers. So let's say, for example, we have, or let's say we have this, HA plus water is H3O plus A. And there we have a balancing number of 2. Let's say there we have a balancing number of 3, just for argument's sake. And let's say here we have a concentration of 0.4 moles per cubic decimeters. This concentration will be 1 because it's a liquid. Yeah, we have a concentration, let's say, of 0.8 and there of 0.2, just for the sake of this example. So now what we would have here is, so that product there, that product has a concentration of 0.8. Its balancing number is 1, so it's just to the power of 1. That product has a concentration of 0.2, it has a balancing number of 3, so it's to the power of 3, divided by this reactant, which has a concentration of 0.4, and it has a balancing number of 2, so it's to the power of 2. But this all always counts only for aqueous solutions and for gases. If either a reactant or a product is a solid, we ignore it in this calculation. And if either a reactant or a product is a liquid, we ignore it for these calculations. So in these calculations, where we calculate the equilibrium constant, we only use aqueous solutions or gases. So in this case, here we have a liquid, so we're not going to take that into consideration for this calculation. Okay, and then we're going to get an answer, and that answer is going to have no unit because it's just concentrations that we've multiplied and divided, and the units cancel. So that's what this means. The equilibrium constant of an acid, of a base, of water. So what's important is that for any acid that has reacted with any base, if we multiply Ka with Kb, then we can always say that H3O, the H3O concentration multiplied by the OH concentration is going to give us Kw, which is the equilibrium constant of water, which is 1 times 10 to the power of minus 14. Okay, so in any reaction, acid and base reaction, the concentration of H3O multiplied by the concentration of the hydroxides will give us 1 times 10 to the power of minus 14. So this is going to allow us to swap between concentrations of H3O and OH. So if we want the concentration of H3O in a certain reaction where we only know the concentration of OH, we can use this formula to determine the unknown concentration. And now from there, we can go to pH or POH calculations. So we just said the hydronium ion concentration multiplied by the hydroxide ion concentration will always give us 10 to the power of minus 14. So if in a certain acid-base reaction we have this one, but we need this one, we can use this formula to determine the unknown. Right. Now, you know what pH is. So we can also calculate POH, where we calculate the percentage of the hydroxide ion concentrations. Yeah, this is the percentage of the the hydrogen ion concentrations. Right. Now, pH is equal to the negative log of the hydrogen ion concentrations. And remember that hydrogen ion concentrations is the same for our purposes as the hydronium ion concentration, H3O+. And POH, the percentage of the hydroxide ion concentrations, is the negative log of the hydroxide ion concentrations in a certain solution. Right. So now, let's say, for example, we have this question where we have to calculate the pH of a solution of 10 grams of calcium hydroxide in 100 milliliters of water. So we first are going to have to calculate what is the concentration of this solution, right? So concentration is mass over mv. C is equal to m over mv. The mass is 10 gram. The molecular mass is, if you look over here, calcium is 40. And then there's 2 oxygens, so it's 2 times 16 plus 2 hydrogens, so that's 2 times 1. So that gives us 74 grams per mole. So that molecular mass is 74. And the volume is given in milliliters. We need to convert it to liters, which is equivalent to cubic decimeters. So that's 0.1. If we calculate that, we get 1.35 moles per cubic decimeters. Now we have the concentration of the calcium hydroxide solution. But now this is where monoprotic and polyprotic, etc. comes in. Here you can see that when this calcium hydroxide dissociates, it's going to form calcium 1 calcium ion, but 2 hydroxide ions, right? If this dissociates in water, then 1 mole of calcium hydroxide gives us 2 moles of hydroxide ions. So if this is 1.35 moles per cubic decimeters, it means we are going to have 2 times 1.35 moles per cubic decimeters of hydroxide ions. So that gives us a concentration of 2.7 moles per cubic decimeters of hydroxide ions. Okay. So this is important to remember. When you have a reaction, an ionization reaction of either an acid or a base, you need to determine that acid or base that is going to ionize, its concentration. And then you have to make sure how many hydroxides or how many hydrogens is this going to release, right? And then you have to multiply its concentration by how many hydrogens or hydroxides it's going to release to give you the concentration of those ions. Now that we know what the concentration of the ions are, now we can say, okay, so POH is equal to negative log of the hydroxide ion concentrations. Now, this is a lot of maths in here, but for our purposes, all you have to know is that this is a little button on your calculator. So you just press the negative button and the log button, and then the concentration that you've calculated. Okay, so don't worry about the maths. Just put it in your calculator. So, negative log of our hydroxide ion concentrations, 2.7. And that gives us, so substituting that into our calculators gives us 0.43. But the question was calculate the pH, not calculate the pOH. But we know this. We know that pH plus pOH is 14. So now we're going to say, all right, pH plus pOH is 14. pH we want to calculate. pOH is 0.43, which is 14. So pH is then 14 minus 0.43, and that gives us 13.57 as our pH. Right. What we could also have done, instead of using the fact that pH plus pOH is 14 and that pOH is minus log of hydroxide ion concentrations is we could have gone back to this statement where we could have said, so we know that H3O multiplied by the OH concentration, in this case 2.7, that's equal to 10 to the power of minus 14. And then we could have used this calculation to determine the concentration of H3O plus. So that would be 10 to the power of minus 14 divided by 2.7, right? So if you then if you calculate this, then you get 3.7 times 10 to the power of minus 15 moles per cubic decimeters as the concentration of that hydronium ion. And now you can go from the concentration of the hydronium ion to the pH, where pH is the negative log of that concentration. So that's negative log of the concentration, which gives you 13.57, which is the same as we got in the previous calculation. So the point is, you can use either this fact that those two concentrations multiplied by each other gives you 10 to the power of minus 14, or that pH plus pOH is 14. Then pH is minus log of hydrogen ion concentrations and pOH minus log of hydroxide ion concentrations. So now, in a certain ionization reaction, you will get one of these two concentrations. From that concentration, you can get pH. From that concentration, you can get pOH. If you have then gotten pOH, but you were supposed to get pH, you can convert to pH with this calculation. Or, if you have, let's say you have that concentration, and you directly go to there, then you can convert with those. So you can use these 4 formulas whenever you have the concentration of one of these and you need either pH or pOH. What's important about the concentrations is that you remember whether it's a monoprotic acid, where a concentration of 1 mole per cubic decimeter will yield 1 mole per cubic decimeter of ions, or whether it's polyprotic, where in this example, where 3 hydrogens will be released for 1 mole of whatever the substance was. Okay, so that's everything that you need to know for acids and bases. Please work through